Hello, and welcome to my next webinar in my series on modern Java by example. Thus far, we've been focusing primarily on concurrency and parallelism mechanisms available with Java Streams, Project Reactor, and RxJava. In today's webinar, however, we're going to start focusing on synchronization mechanisms. In particular, we're going to be focusing on the Java StampedLock, as well as a few other mechanisms associated with various concurrent collections and synchronized collections. So let's go ahead and jump in. First, I'll show you where to find the code, and then we'll start looking through the example. So if we share my screen, first of all, you can see where you can find the code, which is available in my Live Lessons Java 8 folder under the EX9 subfolder. So if you go in here, you'll find all the source code, which has been updated to include some fixes and improvements from previous versions. Now let's go ahead and share my IntelliJ project, and what you'll see is the EX9 main program. And this example is going to showcase and benchmark the use of Java ConcurrentHashMap, a Java SynchronizedMap, and a HashMap that I've implemented to be protected using the StampedLock mechanism. And this will be used to compute, cache, and retrieve large prime numbers. And the particular example, as we'll see later, will be useful when we start talking next week about topics related to back pressure and flow control with Project Reactor and RxJava. So this is kind of a tease for what we'll cover next. This example also covers a number of really interesting features of Java StampedLock, such as conditional writes and optimistic read locks. And we'll also round it out by showing some slicing mechanisms that are available in Java Streams using the takeWhile and dropWhile operations. But let's focus primarily on the synchronizers first. Here's the way the program is designed. We have an atomic integer that we use to keep track of the number of times we have to check to see if a number is prime. And we use this as a way to count the number of duplicates in our randomly generated prime numbers. We're also going to have a list of randomly generated large numbers. And these numbers will be generated according to some parameters we can control programmatically. And that'll give us a chance to try very large numbers as well as smaller numbers to see how that affects the way in which the different synchronization mechanisms work. Here's the main program. We create an instance of the EX9 class, which is what we're in here, and then we go ahead and run the examples. Here's the constructor for the EX9 class. We go ahead and make ourselves the new prime check counter, giving it an initial value of 0, and this counter will be reset every time we run a new test. We then go ahead and parse the arguments, which can be used to control all kinds of interesting options related to the type of strategy used by the StampedLock HashMap manager, the count, the max values, and all that kind of good stuff. We then go ahead and use the results that were set by the options to get the number of integers we should be generating and also get the max value for the random numbers that we're going to be generating. We then go ahead and make ourselves a new random integers collection, which is implemented here as a list. And we do that by generating a stream of random numbers between max value minus count and max value. And the reason we do it that way is so that we can end up having some duplicates. And you'll see why we're going to need duplicates later to illustrate the use of something known as a memoizer. We box up all these random ints into integers and then collect it into a list. And the reason we do this is we want to make sure that all the different tests we're going to run have exactly the same input, so we don't get different behaviors for the different tests because they were working on different random numbers. So we compute all the random numbers ahead of time. Here's the run method. This is where things get fun, and I'm going to give you a quick overview of the overall flow here, and then we're going to start looking at the various synchronizers because that's really the focus. So the first thing we're going to do is we're going to create something called a memoizer. I'll show you what a memoizer is in a second. Memoizer is basically a cache. And we're going to give it a function to run, which in this case is checking to see whether a number is a prime number. And then we're going to give it a map. And the first map we're going to give it is going to be a synchronized map, which is just a wrapper around a regular hash map using collections synchronized map as a factory method to wrap that. And we'll look at what that does in a second. Next, we're going to go ahead and create a memoizer using a concurrent hash map, which is a super duper optimized concurrent collection that's been improved over the years through, I think, Java 5 up to recently, keeps getting better and better. And then the last type of test we're going to run is going to be a memoizer that will have a stamped lock hash map. And we implement the locking mechanism for that. So that'll give you a chance to kind of compare and contrast different approaches to synchronization. Each of these different examples are going to be tested using a test driver. We're going to see how long they take to run. When we're done, we're going to go ahead and print out the timing results and then demonstrate a few cool things with these slicing mechanisms that are available in streams. So first, let's just talk about the different types of synchronizers we're going to be using here. One type is a synchronized map, and you can take a look here. This is the synchronized map factory method that's part of the collections interface, or rather the collections utility class. And here you can see that a synchronized map is basically just a decorator that's going to have a map, basically a regular map, a non-synchronized map like a hash map or a tree map and so on, that's going to be encapsulated and decorated by methods that will synchronize access using the Java synchronized keyword. So you can see here that there's a mutex object that's defined, and we simply use this for its synchronization properties. And so every method in this synchronized map is going to wrap the real method that it's decorating with a call to synchronize on the mutex. So this is obviously going to be thread safe, but the downside is that every locking operation will lock for the duration of whatever the map call is, and there's only one lock. So this is going to be a fairly heavyweight way to do things. The other approach, the next approach we're going to use is using a Java ConcurrentHashMap. And it's beyond the scope of this particular lesson, this webinar, to talk about ConcurrentHashMap. ConcurrentHashMap is super duper cool, and it's designed to be used for heavily concurrent multi-threaded programs where you have lots of threads that are getting and putting elements into the map. And again, it's beyond the scope to talk about this in detail, but it basically has this concept of breaking up the overall locking properties, the locking discipline, into chunks or segments, and then making it possible to be able to have different locks for every different bucket in the hash map. Again, the mechanisms have changed slightly over time, but the idea is as long as you hash to different locations in the hash table, you're likely not to have any contention whatsoever. So it works very well under high contention. And we'll see that when we show the results of the experiments later. There's some really great articles talking about how ConcurrentHashMap is implemented by people like Brian Getz. So if you Google for ConcurrentHashMap implementation, you'll find some good examples. Then the third type of synchronizer we're going to look at is the StampedLock HashMap Manager. And that's the version that I implemented. And this uses a Java StampedLock instead of using a synchronized object, the way that synchronized map works. And we're going to use all kinds of clever strategies that can be used to optimize the behavior of stamped locking. And we'll see how that works in a second. So here's what the StampedLock HashMap looks like. It extends abstract map and implements the map interface. And we only really care about one method here, as you'll see in a second. But you can imagine using all the different mechanisms and methods if you wanted to do a full-blown version of this. What is a stamped lock? A stamped lock is an advanced reader's writer locking synchronizer that came with Java 8, and it allows multiple readers to go forward at the same time. And when a writer comes along, then once the readers are done, the writer gets exclusive access. And whenever a writer's there, that one thread has exclusive access to whatever you're guarding with the stamped lock, whatever you're protecting. But when there's readers, all the readers can go in parallel. So it's a good example of how to improve certain kinds of data structures that are read a lot more often than they're written to. So let's take a quick look at the way this works. We have a hash map, and we have a stamped lock here. And I should probably just make this a map. It doesn't have to be a hash map. So we could have different kind of maps. We could have a tree map and so on if we wanted to. We initialize those fields in the constructor. And there's a bunch of little helper methods here that do things. But this is the method I really want to focus on. This is the famous compute if absent method. Compute if absent is a really powerful feature that was added to Java in the ConcurrentHashMap originally, and then it's been done elsewhere. And I've been doing it here more explicitly than it is in ConcurrentHashMap. But in a nutshell, compute if absent is a so-called atomic check then act method. And what happens is you give it a key, and if the key already has a value associated with the key in the map, then the value is returned. However, if there is not a value associated with the key, then there's a mapping function that's provided, and that mapping function is applied to generate the value associated with the key. And of course, we're going to use this when we're going to be doing our prime number checking, which I'll show you later. But I want to give you kind of a taste of the overall flavor of compute if absent right now. So what we're going to do is take a look at a couple of different ways that compute if absent can be used. And in fact, we're going to see 3 different ways to implement compute if absent using different features of StampedLock. So the first one we're going to look at is going to be just a very simple vanilla version using a read lock, the read lock variant, the read lock mode of StampedLock, and that's the most straightforward one. But honestly, that's really no different or not a whole lot better than just using a synchronized statement. So you'll see it's really not the right way to go if you're looking for speed. The second approach we're going to use is going to be using something called the conditional write idiom, which is a way of being able to start out with a read lock and then upgrade to a write lock. And if you're lucky, the upgrade takes place atomically in a non-blocking way, and you go on your merry way without having to do a lot of extra waiting. If you're unlucky, you have to release the read lock and then reacquire the write lock and do some extra work. And then the third version is one that uses something called the optimistic read lock. And this is perhaps the most interesting one because, as the name implies, it's very optimistic. It assumes that there will not be contention. And if that assumption proves correct, then there's very low locking overhead. And only if there's a lot of contention do you have to pay a price for that. So those are the 3 different models we're going to look at. And we're going to come back shortly and look through each of those when we get to the point where it matters and you understand why we need to use this mechanism in general. So let's pop back here a little bit. And now that I've kind of shown you roughly how the synchronizers are going to be used, let me show you the rest of the driver program, and then we can return and do a deep dive into the different ways of using the StampedLock idioms. So let's come down here and let's talk next about the actual driver program, and that's going to be called by the time test method. And you can see that the time test method is going to use my cool little run timer time run helper method, which is going to go ahead and record how long it takes to run a test given a memoizer and given the name of the test, which we record. So the run timer time run is just a way of recording those things. Then we can print the results out in sorted order in terms of which ones ran the fastest, the slowest when the computations are done. If we come down here and take a look at the run test method, this is really where the interesting processing takes place using the different synchronizers we're talking about. So you can see here we start out by saying, hey, we're going to run this test with this particular test name and this particular count of the number of items to process the number of random integers to check to see if they're prime. First thing we do is we set the counter to 0 because we're going to reset this for every test. And then we have a little stream here. And this stream is done intentionally because when we talk later in upcoming lessons, upcoming webinars about RxJava and Project Reactor, I want to compare and contrast the streams way of doing things, which is synchronous, even though it's going in parallel, versus the way that Project Reactor and RxJava work, because they're going to be able to run asynchronously. And while that is more flexible in some ways, it comes with it the need for dealing with back pressure. So this is kind of a teaser for discussions we'll have later about back pressure. So what we do is we start by emitting a bunch of random large numbers, and then we're going to go ahead and handle each one to check to see if they're prime. And then based on the results we get, we're going to print the results. So that's our little flow. And this particular flow, you can imagine this flow being used for all kinds of different systems. You can imagine getting a stream of stock feeds, for example, and then doing some processing on that and then handling the results somehow. You can imagine having some kind of sensor system like a temperature sensor or a pressure sensor, and you're getting the data in and you're doing some processing and you're going to generate some output. So this type of a flow is actually very common. Now, the way this is going to work, as we'll see in a second when we look at the emitter, is we can either run this flow concurrently or we can run this flow in sequentially. So the way that's going to work is we're going to take a flag that's going to set it to be sequential or parallel, concurrent. And then we're going to go ahead and generate a stream of random integers using the stream factor method on our mRandom integers list. And then if we want things to run in parallel, if the flag is set, we make the stream a parallel stream. Otherwise, it stays a sequential stream. And we return that as the result. So we give back a stream that will either be parallel or sequential. So let's assume, for sake of argument, it's a parallel stream. So then we're going to go ahead and apply the map intermediate operation, and that's going to take every item in the stream, and it's going to check to see if that number is prime. And we're going to take a look at the check if prime method in a second, but you can see it's going to take in the number, which we're going to call the prime candidate, and then we're also going to take in a memoizer. And the memoizer is a very cool little mechanism we're going to look at in more detail in a second. And the memoizer is used to effectively cache the results. So if we've already computed if a number is prime, we don't have to recompute it. We just look it up in the map. So let's go ahead and take a look at check if prime. This is just an intermediate transformation method. It takes in a prime candidate, and it takes in a function, which actually is going to be a memoizer. And we create ourselves a new result object. New result is just a very simple tuple that basically keeps track of the prime candidate and the result of checking if it's prime. And what we're going to do is we're going to pass the prime candidate, and then we're going to apply the memoizer to the prime candidate. And what the apply method, of course, is going to do is it's going to go ahead and use the concurrent, or it's going to use the maps compute if absent method in order to check to see if there's already a value for this prime candidate that's been cached previously. So let's kind of pop down over here, whoops, into the apply method of the memoizer, if I can do that. And it looks like it's getting confused. So let's go over to the memoizer itself. A memoizer is a very clever data structure that I first learned about when I was taking courses decades ago in data structures and algorithms. And then when I read the excellent book, Java Concurrency in Practice by Brian Getz and Doug Lee and David Holmes and other folks, I discovered the use of memoizers there as well. And what's funny is when the book was published, clearly the publisher got confused and called it a memorizer, not a memoizer, but it's memoization is the right term. And you can find out more information about memoization at this Wikipedia link. So basically what a memoizer is, it's a cache, and it's going to use the map we pass in and a function in order to be able to do memoization. And we're going to pass in, of course, ConcurrentHashMap, a synchronized map, and our fair semaphore hash map. And that's going to be used as the memoization cache. So let's take a quick look at the code. You can see a memoizer is a function, so it implements the function interface, which is a functional interface that was originally introduced in Java 8. We cache the map that we're using as the cache. We cache the function we're using, which is used in conjunction with compute if absent. And then down here we have memoizer, which is the constructor which stashes away the function and the map. Okay, so far so good. The apply method is the thing that does the heavy lifting. And you can see heavy lifting in this context really is just about forwarding to the cache's compute if absent method. So again, depending on whether we're using a concurrent hash map or a synchronized map or the stamped lock hash map, compute if absent is the thing that's going to be called. And what that's going to do is it's going to look up to see if the key already has a value, in which case we get it back. Otherwise, it's going to apply the function in order to compute the value, store it, and then return the value. And we're going to focus, of course, primarily on the stamped locks, the stamped lock hash maps compute if absent method, because that's the cool one that we outlined earlier. So that's what's happening there. That's what a memoizer is. We've also got a way to remove key value pairs, and we have a way to return the number of elements in the cache. And then we also have a way to get the cache itself, get the map. And you'll see why we need that a little bit later. Okay, so that's what the memoizer is. Memoizers are very useful things to have, and that's why I created a little helper class here to demonstrate this concept, because you may find it useful in your own work. So that was check if prime. And then the last thing here, which gets called in the for each terminal operation, is handle result. And all it does is it checks to see if the number was prime or if the number had factors, in which case it prints its smallest factor. So that's just a diagnostic aid to get a result that comes out. Okay, let's see if there's anything else interesting to talk about in the driver program. I think we've pretty much covered all the different mechanisms. Let me show you what happens. Oh, here's the isPrime method. This is the one that checks if a number is prime. And if it is, it returns 0. If it's not, it returns its smallest factor. This is intentionally designed to be inefficient. There are much better ways to compute prime numbers, but I wanted to come up with something that burned CPU time just to illustrate why a cache can be beneficial. We'll talk about demonstrate slicing when we get to the end. I don't want to get distracted from the synchronizer stuff right now. Okay, so if we were to run this program, let's go ahead and run the program. And you'll see that we can set some values here. What I've done is I've set the number of iterations, the number of random numbers to generate, to be 10,000. And then I set the maximum value to be 20,000. And then I'm going to set the strategy for the lock, the stamped lock, to be the right lock variant, which we'll look at in more detail. So if that's what I set, then I can go ahead and run the test. And you can see it should start up. And for 10,000 numbers, it had about 3,690, or it had exactly 3,690 duplicates. Duplicates are good because that is what shows our cache. And it had about 6,310 unique values. And you'll notice that we have the same results for every one of the tests. So that shows the synchronized hash map works like the concurrent hash map, which works like the stamped lock hash map. They're all working correctly. And you can see here that concurrent hash map is the winner. It's usually the winner. Stamped lock hash map comes in a close second. For certain kinds of data, it usually comes in a close second. Sometimes it wins, but it's usually a close second. But our poor synchronized hash map implementation just sucks because it's locking the entire object for every call. So that means there's one lock, there's one point of contention. It's very inefficient. It doesn't scale as the number of threads grow. You can also see what we get back as a result. We print the contents of the map sorted by value, so all the random numbers come first. And then after that, we have, we're going to print out the primes and also the non-primes and their smallest factors. Just for kicks, before I show you a bit more, let's run this test with a different set of options. So let's move and use, say, the conditional write version of the stamped lock. And we'll look more at the implementation in a second, but I just want to see if it makes any difference in performance. So you can see it didn't really make a whole lot of difference for this run. Let's go ahead and try the version that uses the optimistic read lock. And you can see that that's a little better. They're all roughly the same. And one reason they're all roughly the same is that this particular test program doesn't have a whole lot of contention. And so it just happens that that's the way that it works for smaller numbers. If we go up here and we have much larger max values, so if we make it much larger max values, then we should see some more interesting behavior. And what happens when the values get larger, of course, is it takes a longer amount of time to check to see whether or not they're prime. And what will happen is if they have these large numbers that have to be checked to see if they're prime, then all the threads are going to be busy doing those computations. And as a result, there's going to be a lot more contention. In fact, I may have given that number a little too big. It'll take too long to run. Let me go ahead and stop that and crank it down a bit. Oh, I know what I need to do. If I have larger amount of numbers, I need to do a smaller number of iterations. This should work better. So what we're going to do here, now you can see, we only had 100 numbers. They were much larger, though. And now you can see that, interestingly enough, the stamped lock HashMap memoizer, which is the one that uses the version of the strategy that has optimistic read locks, that actually is outperforming the concurrent HashMap memoizer. And they're both doing better than the synchronized HashMap, but it's not such a big win. Let's go ahead and change this back to the right lock variant and just see what the behavior is. See if it makes much difference. We'll see if concurrent HashMap starts to win. So as I expected, when we got rid of the optimistic read variant of this, then the concurrent hash map version works better because its behavior is just more consistent and more optimized. It's not relying on the particular strategy of the stamp lock. Okay, so but you can kind of get a feeling that changing these strategies changes the performance. So with that in mind, let's go over now and look at the stamp lock implementation and see the different strategies we're talking about. So the first strategy we're going to talk about, which is the one you get if you give a W for write lock, that's just a straightforward write lock. And this is pretty much like a synchronized block. So here's how compute if absent write lock works. And this will also give you kind of a feel for what's going on in the hood with compute if absent in general. This just happens to be the one that's using the implementation based on stamp lock. So we come in here, we grab a write lock. So we have exclusive access. That's why we typically think about write locks as pessimistic. They expect there to be contention, and so we need exclusive access. We come in there, we call get on the underlying map, the hash map, and if this is the first time in, get will return a null value, which means I don't have a value yet. So in that case, if we don't have a value yet, we have to call the mapping function, passing in the key, and we'll get back the corresponding value. If the value comes back as null, then the mapping function has gone awry, so we don't put that in the map. But if the value that comes back from apply is non-null, we go ahead and put that value into the map under that key or associated with that key. So now we have a mapping. And what we do then is we return the value, which is either the original value that get returned if we had it there already, or it's the one we just computed using the mapping function. And then the last thing we do on the way out is we unlock the lock. So this is a read lock, this is a write lock. So we're going to unlock the write lock. And you can see this is not that dissimilar to just having a synchronized statement over the entire method, or just making the method synchronized for that matter. It's just using the stamp lock, write lock as that way of doing things. So you might expect that this approach is very pessimistic, so it always grabs a write lock. But we don't always need to grab a write lock. And that's the whole beauty of readers writer locks like stamp lock. So let's take a look at a way that can use this distinction between read locks and write locks. So here's compute if absent conditional write. And what this does is it starts out with a read lock. And read locks are nice because they don't require as much synchronization. In fact, if there's multiple readers coming through at the same time, they're all going to grab read locks initially. They can all proceed in parallel. And what's going to happen here is with the read lock held, we're going to do a get operation. Get is obviously a read. It doesn't change anything. And we get back a value. Now, if what we get back is a non-null value, that key already had a value, and then we just go ahead and return the value. And that's perfect because that meant we never needed to acquire a write lock at all. So that's the happy path, right? That's the fast path through this. And you can see when we return, we have a try finally block way down at the end, which will unlock the lock, which could either be a read lock or a write lock. Right now we know it's a read lock, but other paths to the code, it could be a write lock. So we use the unlock method. And I should also briefly say that when you call read lock or write lock or try optimistic read on stamp lock, you get back something called a stamp. And think of a stamp, think of it basically as a timestamp. It's more than a timestamp, but it's basically keeping track of when that call was made. And you'll see why we need to know that time when we come back later and look at the optimistic reads. It's not really a timestamp, but it's like a timestamp. It's like a generation count. So let's assume for sake of argument we didn't already have a value. So the value equaled null, which was the signal from get that the key didn't have a value associated with it yet. So what we're going to do now is we're going to go in here and we're going to use a for loop. And you'll see why we use the for loop, just to avoid repeating code unnecessarily. The first thing we're going to do is we're going to try to convert that read lock to a write lock. And this is what makes this a conditional write lock. So we're going to use the try convert to write lock method on stamp lock. And this is a non-blocking operation. If it's the case that currently there are no writers, and there's also no readers, we can go ahead and do that upgrade. So we're going to end up with a write stamp, which says it's a write lock. So if you succeed, then the value is non-zero. So if we manage to do the upgrade atomically, then we stash away the write stamp in the stamp, to simplify the later unlock operation. And with the write lock held, we now go ahead and apply the mapping function on the key and get the value back. And notice that we have to be very careful here to make sure that we only do this mapping function one time, because we don't want to keep redoing it over and over again. That'll cause confusion. And if you don't have idempotent mapping functions, in other words, if they don't always return the same result, then you'll have confusion there too. So what we're going to do is we're going to go ahead and see what the result was. If it turned out to be non-null, we're going to put it in the map, and then we break out of the loop, and then you can see we're going to go ahead and return the value and unlock the lock, which at this point will be a write lock as opposed to a read lock as it was in the previous case. If for whatever reason we can't do the automatic conversion, then we're going to go ahead and unlock the read lock. We say, uncle, we give up, we can't do our optimization. Then we call write lock, which will block in order to wait until it can get the write lock exclusively. So there could be a blocking period there. And during that time, some other things may have changed. In fact, someone else could have come along and given a value for that particular key. So if that happens, when we get the write lock, we check to see whether there is a value associated with the key now, because some other thread could have looked up the same prime number and added the same number and added whether it was prime or not to the map. So if the value is null, that means nobody has actually done this mapping yet. So in that case, we're going to continue, which will loop back around here, try to convert to a write lock. And if we're successful, we apply the mapping function, and then we put the value into the map. So that's why we're looping, just to avoid having to rewrite that code. We just kind of jump back around again and loop. Otherwise, if the value that came back from get is non-null, that means someone else has associated a value with that key. So we are no longer on the hook to do that. We're just going to use the value that came back from get, break out of the loop, and return it here. So that's the conditional write strategy. And if you read the documentation for StampedLock, you'll see an example sort of like this, not quite as cool as this one, of course, but it's sort of along the same lines. So the third approach I want to talk about is compute if absent optimistic read. And this is the most optimistic approach. So this approach was sort of optimistic because it said, well, if there's already a value associated with the key, then let's only need a read lock, no need to get a write lock. This approach we looked at first is very pessimistic. It says we're always going to get a write lock. So that's going to be the worst in terms of dealing with optimism. Keep hope alive. Keep your hope for not having to do a write lock alive. And then down here is the very optimistic version. And this is interesting. And I added some extra cool things here to demonstrate the idea of being able to do multiple attempts at optimistic reads. But let's kind of walk through this and see what happens. So we come in here and we define some local variables. And you'll see why we need to have these local variables defined kind of at the top here. We define a stamp. We define the value. We get an option that says the max tries. This is the number of times to try to do this optimistically. And then we also have a variable called tries, which we initialize to 0. And you can see here, now we go into a loop. And we're going to try up to the max tries. So the default max try is 2. But you can set that programmatically with the -t option to whatever you want. You can make it 1. You can make it 100. That's probably overkill. But the point is you can control the number of tries. And so what happens here, we come in and we grab an optimistic read lock. And that's kind of a euphemism. An optimistic read lock really isn't a lock at all. It's basically just an indication of a timestamp, if you will, of when we came in and tried to acquire something in an optimistic way. And the reason why this is important is it doesn't actually do a full cache flush. So it's very, very lightweight. And there's pros and cons to that, as we'll see in a second. We then go ahead and with the optimistic read lock held, using that word loosely because nothing is really being held, we get the value of that's associated with the key in the map, in our case in a hash map. And then we check to see, did anybody come along in this little tiny window and acquire the lock for writing? And if the answer is no, they did not, then the validate stamp method will return true. So that says the value we have here was not changed because no one grabbed a write lock. The assumption is if they grabbed a write lock, the value could be changed. So in that case, we break out, and then we're going to go ahead and do some other stuff. But if for some reason it turns out that the write lock was acquired in that little tiny window of time, then validate returns false, and we're going to loop back around again, and we're going to do this process up to max tries number of times. So if you're feeling lucky, you might get lucky, and you might find that window where you actually get a valid version of the value associated with the key. Now, what happens here is if for some reason a write lock was acquired, there is no guarantee that value has any meaningful information in it whatsoever. It could just be randomly garbage for that matter. So for that reason, you shouldn't ever check the value of value, the return value, or anything that's done inside here unless validate succeeds. So let's say that we don't get lucky and we aren't able to actually optimistically read this value after max tries. In that case, we just revert back to using the compute if absent conditional write strategy, which we've already seen, and it works fine. It just is not quite as optimized. However, if we got lucky and we've got a valid value, and that value is non-null, well, in that case, we're just going to return it. And talk about optimistic, we never acquire a lock in that case, right? We were able to magically read the value with no contention. We never grabbed a read lock, and it just returns right away. So particularly in situations with low contention, then this locking strategy is going to do very, very well. Let's assume for argument, however, that this was the first time in. Then at that point, we're going to try to convert the optimistic read stamp to a write lock. And that's a pretty big jump. But if we're lucky and it works, then we're going to go and do the stuff down here. If we're unlucky, if we get back a 0, that means we didn't manage to do that conversion atomically. Well, in that case, then we're going to have to drop off or drop back, and we're going to fall back again and revert to using the conditional write strategy. But let's assume for sake of argument that we were lucky. It did actually do the atomic updates. Well, in that particular case, then we're going to go ahead and check to see if the value is null, and we're going to go ahead and put the value into the map after, of course, first applying it. So we only apply the mapping function with the write lock held to guarantee it's only called one time. And then on the way out here, you can see that we have a try finally block, which will unlock the write lock. So we know it's a write lock at this point, and that's the only lock we're ever going to have to release. You never have to worry about unlocking an optimistic lock, optimistic read lock, because there was no lock acquired in the first place, which is pretty cool. Okay, so I think that's pretty neat. This is a really fun example that demonstrates how to do these different approaches. And let me go and kind of with all that stuff in mind, rerun a few tests real quick. So if you go up here and we zero everything out to its default state, what happens when we run the tests is by default, we're going to have 100 iterations using max integer, which is a big number, as the maximum range. So these are going to be some big honking random numbers to check to see if they're prime or not. And so this will take a while to run. You can see here we had 61 unique values where we had to do a prime check, and 39 duplicates, which is about the right number. And you can see again that it's taking a while to chug away and do all the computations. We'll get the results in a second. What I wouldn't be surprised to see is that ConcurrentHashMap does well, and then the other two do less well, but most likely synchronized lock will do the worst. That just sort of tends to be the way things work. Oh, this is interesting. So in this case, you can see that StampedLock actually did pretty well, which is surprising. But you'll also notice that they're fairly close together in terms of runtime performance. And that, again, is because these large prime numbers, or these large numbers, take so long to check for primality that all the threads are spending a lot of time in the mapping functions trying to compute them. And so as a result, it just takes a while to run. And there isn't that much of a difference. But as I mentioned before, if we come down and we make the numbers much more sane, like we have 1,000 numbers and the max value is, say, 10,000, then we're going to see this. First, it's going to take a lot less time to run. And here again, the concurrent HashMap and the StampedLock run about the same. So interesting stuff. I think as a general rule of thumb, ConcurrentHashMap is really probably the thing to go with in general because it's very well optimized and tested. But I think it's also fair to say that the StampedLock version works surprisingly well, given that it's not anywhere near as sophisticated as the ConcurrentHashMap implementation, which uses really clever low-level mechanisms like compare and swap operations that are available at the Java unsafe level. So now that we've talked about the synchronizer mechanisms, especially the ones in the synchronizer mechanisms, particularly the ones in StampedLock HashMap, let's go ahead and turn our attention back to the driver program and show how you can do slicing with the takeWhile and dropWhile methods in Java streams. So let me go ahead and share my screen again. And this time we're going to share the IDE. As you can see here, after running all the tests and getting the results, we call a method called demonstrate slicing. And in this particular case, we happen to pass in the StampedLock HashMap as the parameter, but we could have used anything we want there, any of the different maps, synchronized map or the concurrent hash map and so on. So let's see how demonstrate slicing works. We're going to take the map, and the first thing we're going to do is we're going to sort the map comparing by value. So we're going to end up basically with something that we can iterate through, and it'll put all the zeros, all the prime numbers at the beginning of the map, followed by all the non-prime numbers. So we're sorting by value. Remember that the first value is the key is the prime candidate, and then the value is either 0 if it's prime or the smallest factor if it's not prime. So let's take a quick look at sort map because it shows a real clever technique we can use here. So we go ahead and take the map and we turn it into an entry set. So that's a set of basically entries, which are prime candidate to smallest factor values. We turn that into a stream. So now we have a stream of entries, and then we sort them by the comparator, which in this case is comparing by value. So now we have a stream of map entries that are sorted by value, not by key. And then we go ahead and we collect that stream into another map. So what we're going to do here is we're going to have the key for this new map be the key in the map, and we're going to have the value be the value in each map entry. And then we're going to use the linked hash map as the implementation of this new map. Before, we had a StampedLock hash map or a concurrent hash map or a synchronized hash map or whatever. Now we're going to use a linked hash map. And a linked hash map is interesting because what it does is it puts things into the hash table by hashing, but it keeps track of the order in which things were inserted. And since we're inserting these things in sorted order by value, then when we iterate over through this thing later using a stream, we're going to get the values in the sorted order by value rather than in terms of however they happen to hash in the map. So if we go back, you can see that after we have sorted everything, we then go ahead and print out the sorted map. And if you look at the example here, you can see, for instance, we sort by the by value, so all the prime numbers come first. And then let's go over here real quick and pop back to the code. So what we're going to do now is we're going to print the prime numbers followed by printing the non-prime numbers. So let's see how we can do that. It's a really clever little technique. So what we're going to do here is we're going to take our newly sorted map, sorted by values, turn it into an entry set again, convert that into a stream, and now we're going to use the takeWhile operation. And takeWhile is a Java streams intermediate operation that's short-circuiting and stateful. And what we're going to do is we're going to take from the stream as long as this predicate is true. And this predicate says, hey, as long as the values equal 0, keep taking the elements in the stream. So what we're basically doing here is we're taking all the values in the stream that are primes, and then we're going to map that stream of map entries into just a stream of keys. So it's a stream of integers, which we collect into a list, and then we go ahead and print the prime numbers. So that's how we printed the primes. We just basically kept taking while the value was equal to 0. Here's how we can print the non-primes. Basically the same algorithm structure. The difference being that instead of using takeWhile, we use dropWhile. So what dropWhile does, as the name implies, is we go through the series of entries and we ignore everything that has a value of 0. So we're skipping over all the primes. So once again, dropWhile is kind of the sibling of takeWhile in the sense it's short-circuiting, it's stateful, except it will drop everything. And once the condition stops matching, then it'll take the rest and basically give a stream back of all the other elements, which in this case would be all the non-primes. So I think that's kind of a clever technique. It's also worth noting that takeWhile and dropWhile differ from the filter operation in a stream, even though they seem superficially the same at first, because filter has to inspect every element in the stream, whereas takeWhile and dropWhile can stop once the conditions are no longer matching. So anyway, just a little cool example that will hopefully round out the rest of the discussion here, showing a cool Java Streams feature we really haven't touched on a whole lot before. Okay, so I think that's probably what I want to cover today. If you have any questions, obviously feel free to leave them at the bottom of the in the comments section on the video. And I think you'll also hopefully get a good sense of how this code works if you have a chance to play around with it and try it out yourself. Everything's been pushed to my GitHub repository, and so you can play around with this to your heart's content. Where we're headed with this in future weeks is I'm going to come back and re-implement this style of program using Project Reactor, most likely, because I've come to like that a little better than using RxJava. It's just cleaner and more modern Java-ish in its own way. But what we're going to do is we're going to be running the emitter in its own thread, and then we're going to have the subscribers running in different threads. And because the computations that are taking place here are going to run for a while, what you'll see is if the emitter is emitting quickly, then the subscribers are not going to be able to get the data because things are going to be queued up along the way. And we'll be able to watch the queues grow and grow and grow. And obviously, in a real program, that will cause problems because you'll run out of memory eventually if producers or if the publishers are generating data faster than the consumers or subscribers can react to it and do something with it, consume it, then you've got a problem. So we're going to talk about how back pressure can be used in Project Reactor through the flux mechanism, or you could use flowables if you're an RxJava person. And we'll show how to alleviate that problem with the data being queued. So that'll come later. And the other thing we're going to do is, because we've got this clever memoizer that's passed in as a function, we're going to be able to replace the use of a memoizer with simply the actual function we wanted to compute. So what you can do here is, just as an example, instead of saying new memoizer, you can just say this is prime, and then all the code here, comment that out. What we'll see when we look at this, you can do stuff in a way where you'll be able to toggle back and forth very easily between the function and the memoized function. And that's cool. Why is that cool? That's cool because it's going to be able to allow us to show what happens if you have really long-running computations like prime number checking, and you don't have the ability to cache things to speed them up in some situations. And that, of course, would also affect back pressure. And we'll talk about that when the time is right. So with that, thank you very much for watching the video. I, at this point, have a Twitter account, so you can follow me there. And if you have any questions, please let me know.